Alright, this is a video on concavity and the second derivative test. So we're going to start off with a little bit of background on concavity and what concavity is. Alright, the definition of concavity. Let f be differentiable on the open interval I. The graph of f is concave up if f prime is increasing. The graph of f is concave down if f prime is decreasing on the interval. So concavity refers to the rate of change of the derivative. So a graph is concave up if the derivative or the slope is increasing. A graph is concave down if the derivative or the slope is decreasing. So concavity refers to how the derivative is changing. So anytime you hear concave up, you should think the derivative is increasing. Whenever you think concave down, the derivative is decreasing. So concavity tells you how the derivative is changing. That's the first thing that you should think of. Concavity, how is the derivative changing? So let's kind of do a visual so you can connect this. Now back in algebra 1, 2 in geometry, or in algebra 1 and 2 in pre-calc, you might have referred to parabolas as being concave up or concave down. So let's kind of look at this one first. So this graph is concave up. So I want us to first look at, we're going to look starting from left to right. All right, if you look from left to right, right here, if I draw in my tangent line, like maybe at this point right here, I can see that the slope of my tangent line right here is negative. All right, and that's a very steep negative. Now, if I draw another tangent line and I look at the slope right here, or the derivative at this point, I can see right here that my slope would still be negative, but it's less negative. So my slope went from very negative to less negative. All right. Now, at this critical point right here, I know that my slope is 0. So my slope went from very negative to less negative to 0. Now, if I draw in my tangent line to the point right here, my slope is now positive. And now if I draw in the slope of my tangent line maybe at this point right here, my slope is very positive. So my slope went from very negative to very positive. We're going to say f prime, or the slope, is increasing here. All right. So my slope went from very negative to very positive. My slope went from negative to positive. We can say f prime increased over this interval. So anytime your slope is going from very negative to very positive, you can say that a graph is concave up. All right, so our slope is changing. It's becoming more positive. Now this graph being concave down, if I draw in a tangent line right here to this point, let's do it right here. All right, the tangent line to this point. All right, I can see my slope is very positive right here. All right, at the point right there. All right, now let's draw in another tangent line right here so I can look at the slope of my graph at this point. My slope is still positive, but it's less positive. Now, right here, my slope is 0. So my slope went from very positive to less positive to 0. Now over here, if I draw in my tangent line, the slope of a tangent line right here is now negative. And then let's do the last one right here. Now it's very negative. So this graph we say is concave down because the slope or the derivative is decreasing. it's going from positive to negative. So whenever you're talking about concavity, it's how is the slope or derivative in parentheses changing. So that's what you're thinking about when you're looking on the graph. So now, we have a test for concavity. We're going to use second derivatives to analyze concavity. So let f be a function whose second derivative exists on an open interval I. If f double prime, the second derivative, is positive, then the graph is concave up. If f double prime is negative, then the graph is concave down. So you can use the second derivative to figure out concavity. If the second derivative is positive, it's concave upward. If the second derivative is negative, it's concave downward. So what that means is if the second derivative is positive, the derivative is increasing. If the second derivative is negative, the derivative is decreasing. All right. Now, a point of inflection is a point where the concavity changes. So where the graph goes from being concave up to concave down, or concave down to concave up. All right. So, and then a point of inflection occurs where f double prime of x equals 0, or f double prime doesn't exist. All right. So it's similar to critical values, but now we're using the second derivative when we're finding points of inflection and concavity. So let's go ahead and do an example with this. All right. The second derivative, or actually we're not there yet. We're on here, example 1. Determining concavity. All right. Determine the open intervals on which f of x equals 6 over x squared plus 3 is concave up or concave down. State any points of inflection. All right, so this means we're going to use the concepts from the previous page. I need to figure out if it's going to be concave up, the second derivative is positive. It's going to be concave down, the second derivative is negative. So let's go ahead and do that. So first step is let's find our second derivative. All right, find second derivative. You got to always keep in mind the rules here. So especially product, quotient rule, etc. All right, so I have f of x equals 6 over x squared plus 3. Let's just use the quotient rule. You could also bring this up to the numerator and use the power and chain rule, but I'm just going to use the quotient rule. So f prime of x equals, the derivative of 6 is 0 times x squared plus 3 minus 6 times the derivative of the denominator is 2x all over the quantity x squared plus 3 squared. Let's keep going. That's going to give us in the numerator negative 12x because this is going to cancel. So I have negative 12x over the quantity x squared plus 3 squared. Now, the thing is, though, that's only the first derivative. I'm looking at concavity. So because of that, I need to find the second derivative. So now I got to use the quotient rule again. All right, to do that, the derivative of negative 12x is negative 12 times the denominator, x squared plus 3 squared, minus the numerator, negative 12x, times the derivative of the denominator. Now, the derivative of the denominator, let's do that on the side real quick. So ddx of x squared plus 3 squared is going to equal 2 times x squared plus 3 to the first power. I brought the 2 down. Now I apply the chain rule and bring the inside out and take the derivative, so times 2x, which gives me 4x times x squared plus 3. So I'm going to write that right here, times 4x x squared plus 3. I left it factored for a reason. All over x squared plus 3 squared to the, all right, so now I'm squaring the whole denominator of the previous problem. When I do x squared plus 3 squared, because that's what was in the previous problem, I'm going to have x squared plus 3 to the 4th power. Now from here, this looks a little bit messy. So what I can do, all right, is in the numerator, I'm going to try and factor out a greatest common factor. So I see that both terms have a negative 12 in common. All right. I see that both terms have an x squared plus 3 in common. So I'm going to factor out negative 12 times x squared plus 3. Now, when I bring an x squared plus 3 out of x squared plus 3 squared, I'm just going to have x squared plus 3 to the first power minus, all right, I factored out this x squared plus 3 and I factored out the negative 12. So I just have x times 4x, which is 4x squared, all over x squared plus 3 to the 4th power. I can still simplify inside the brackets. X squared minus 4x squared is negative 3x squared plus 3, all over x squared plus 3 to the 4th power. All right, so now I finally have my second derivative. All right, to review where we're at so far. First, I took the first derivative, and I got negative 12x over the quantity x squared plus 3 squared. Then I took the derivative again using the quotient rule. But when I used the quotient rule, I had the chain rule involved, and I had to square the denominator again. I now factored out the greatest common factor and simplified. So now, step 2. All right, so we have to find where f double prime of x equals 0, or where f double prime of x does not exist. So let's take a look. If I look up in the numerator right here, actually we can actually look back real quick. So what I can actually do, I should have done this in the last step. So if I look at f double prime of x equals negative 12 times the quantity x squared plus 3 times negative 3x squared plus 3 over this quantity, I can actually simplify. This x squared plus 3 cancels with one of them down here. So now I have negative 12 times the quantity negative 3x squared plus 3 all over the quantity x squared plus 3 to the 3rd power. Now what I can do is factor out a negative 3. If you factor out a negative 3, I'm going to have negative 12 times negative 3 times x squared minus 1 over x squared plus 3 cubed, which is just 36 times x squared minus 1 over x squared plus 3 cubed. This is kind of a messy problem. All right, so now we have our second derivative. This is our simplified second derivative. All right, so now I have to find out where my second derivative equals 0 or my second derivative does not exist. So my second derivative was equal to 36 times the quantity x squared minus 1 over x squared plus 3 cubed. All right, so if I look at my denominator, there's no x value that's going to make the denominator 0 because I'm going to square something and then add 3 to it. This denominator will always be positive. A number squared plus 3 will always be positive. There is no value that will make the derivative not exist. All right, so that's not going to apply here. But I can find where the second derivative is 0. So I'm going to take 36 times the quantity x squared minus 1. All right. I'm going to set it equal to 0. Just factor real quick. I got 36 times x minus 1, x plus 1 equals 0. So my two values are 1 and negative 1. All right. Now we're on step 3. All right. So to review, we found the second derivative first. Then I found where either the second derivative was equal to 0 or it did not exist. Now, step 3, we got to test for concavity. So first thing I'm going to do is I'm going to plot those values of the second derivative on a number line. All right, so my values that gave us a second derivative equaling 0 were negative 1 and 1. Now let's make our intervals. So I have negative infinity to negative 1, negative 1 to 1, and 1 to infinity. All right, now we got to choose test values. So I'm going to choose x equals negative 2, x equals 0, and x equals 2. Now, since this time I'm testing the concavity, all right, I'm testing whether the graph is concave up or down. I'm checking the sign of f double prime of x. You can put an underline, a box around that. This is different. I'm asking in this problem about concavity, so I'm looking at the second derivative. So let's go ahead and do that real quick. So our second derivative was negative 30, or it was positive 36 times the quantity x squared minus 1 over x squared plus 3 cubed. So let's test f double prime of negative 2. That's going to give us 36 times negative 2 squared minus 1 over negative 2 squared plus 3 cubed. So it's going to give us 36 times 4 minus 1 over 7 plus 3 cubed. I can already tell I'm only going to have positives left. 36 times positive 3 over 10 cubed, so it's going to be positive. Let's test f double prime of 0. So I'm going to have 36 times 0 squared minus 1 over 0 plus 3 cubed. That's going to give us 36 times negative 1 over 27. That's going to be a negative. All right. So we have a positive, a negative, and then let's do the last one, f double prime of 2. 36 times 2 squared minus 1 over 2 squared plus 3, that quantity cubed. That's going to give us 36 times 4 minus 1 over 7 plus 3 cubed, and I'm still going to get a positive. All right, so now we need to draw our conclusions. All right, our conclusions. You have to be really careful from here on out. I was looking at the sign of f double prime. So because f double prime was positive, our graph is concave up, or the slope is increasing. F double prime is negative, it's concave down. F double prime is positive, concave up. So let's check if we answered the full question. Determine the open intervals on which f of x is concave up or concave down. So it's concave up on negative infinity to negative 1 and 1 infinity, because make sure you have your justification, f double prime of x is positive, concave down on negative 1, 1, because f double prime of x is negative. Now, we almost answered the whole question. It says, state any points of inflection. A point of inflection is an ordered pair where the graph changes concavity. So it's where the graph changes from concave up to concave down, or concave down to concave up. So I can see here the graph goes from concave up to concave down. There's a change in concavity. At x equals negative 1. And it goes from concave down to concave up at 1, and at x equals 1. But it says a point of inflection means you have the x and the y. So what I'm going to do from here is plug in the negative 1 and 1 to the original function. I need an ordered pair. So my original function was f of x equals 6 over x squared plus 3. So let's find f of negative 1. All right, that's going to give us 6 over 1 plus 3, which is 6 over 4. That gives us 3/2. So our first point of inflection is negative 1 3/2. Let's find the other one. F of 1, we'll have 6 over 1 squared plus 3. That's 6 over 4, which is 3/2. So I also have 1 3/2. So these are our points where our graph changes from being concave up to concave down. So these are the points of inflection. All right, so this problem should have two answers. All right, first, I'm going to box the first one. It's concave up on negative infinity to negative 1 and 1 to infinity because our second derivative was positive. Concave down on negative 1, 1 because our second derivative was negative. I also asked for the points of inflection. That's where the concavity changes. So our points of inflection were where the x values of where the concavity changes, but I had to plug it in and get the y values. So negative 1 3/2 and 1 3/2 are our points of inflection. All right, to review, in this video we started with talking about concavity. and what graphs that are concave up and concave down look like. We talked about the test for concavity. So if the second derivative is positive, the graph is concave up. Second derivative is negative, it's concave down. A point of inflection is where the graph changes concavity. So it goes from upward to downward, concave upward to concave downward, or vice versa. Points of inflection happens where the second derivative is 0 or the second derivative doesn't exist. Our steps to finding concavity were find the second derivative. We might have some special factoring techniques. Find where the second derivative equals 0 or doesn't exist. And then perform the test for concavity using intervals and test values. And then making sure you answer with a justification, and you also state your points of inflection if you have any. All right, this concludes the video, first video on concavity and the second derivative test.